Welcome back, students. So this is what we have at this point of time. So we have a load capacitance. So this is the load capacitance, and we have an inverter where the input voltage is given, and we need to find out what is the output voltage profile with respect to time. So basically, we want to find out the transient analysis. So what we need is, as I've drawn here, the output, the input voltage. So this is the input voltage, and this is the output voltage, V of B, that is the voltage at the node B with respect to time domain, and the x-axis is the time domain. Right. So what we need is how is the output going to fall, or how the output is going to rise. Right. Remember that we have considered the input voltage as a step voltage. So we need a step response. So the output voltage, what should be the response for a given step input voltage? At this point of time, I know, although I've written it as a linear profile and an exponential profile, don't worry about it. At this point of time, we will understand what this linear profile and an exponential profile. It is very simple. It is this particular profile starting from this particular point to this particular point. It is a linear line, linearly decreasing line, output voltage profile, and then starting from this particular point, it is an exponentially decreasing profile. Right, so we will have to see how the capacitance discharges, how the capacitance is discharges given an input voltage here of VDD, how the capacitance of the output, capacitance at the output node discharges. Right, so what in this particular profile, there is one more important aspect. So let me point it out. When the input voltage is actually 0, when the input voltage is 0 volts or the digital logic 0, we know the inverter output has reached a steady state of 1 volts or a logic 1. Right? And then as the step input is applied to VDD volts, to the VDD value, right? It may be a 1 volts or 5 volts, whatever it is. The output voltage of the inverter, because the input voltage is now 1, the output should eventually reach to 0 volts. So that means starting from 1 volts, right, as an initial condition, it should go down to 0 volts. So at the steady state value, it should eventually reach to 0 volts. So the transition from 1 to 0 volts is our transient analysis, and that is where we will try to extract the delay parameters. Right, so there is a delay here for this inverter circuit given an input voltage of 0 to 1, the change in the logic from 0 to 1. The output voltage doesn't change rapidly from 1 to 0. It actually takes some time for the output voltage to change from 1 volts to 0 volts. And that particular change in the duration of the time is what we will extract it, or we will characterize it as the delay parameters. Right? Hope this particular, the intention of the inverter circuit and then extracting the delay parameters is clear. Moving ahead, let's begin with our discharging profile of the capacitors, our understanding of the discharging profile of the capacitors. So if the input voltage is actually 0, that is the initial condition. So this is my initial conditions. Okay. My VB of T, the output voltage here is at VDD, that is at steady state for the previous condition. And when the input voltage switches from 0 to VDD, that is the step input is applied. And in that particular case, when the input voltage and at this particular gate, when it is set to VDD, after applying that step input, VGS value on the PMOS side is actually 0. There is a VDD on the gate side, source side is also VDD. So this particular PMOS will be off. Right? On the NMOS side, this is VDD. VGS is VDD minus 0. So this NMOS should be on because it is much, much greater than VD. So it has to be either in the linear region or the saturation region. Right. So for this particular analysis, we will consider the long channel current model. Just to simplify the things, we will consider long channel. And in this particular lecture, we will consider only the long channel, right, and not the short channel current model. Okay, so moving further, so NMOS is on, that's what we have highlighted. The VGS for the NMOS is nothing but VDD minus 0, which is VDD. VDS VDS initially, right, when V input voltage is 0 volts, initially when it is at 0 volts, we know that the output voltage starts from VDD and then it discharges to 0 volts. Right, so initially at the time t is equal to 0, when it is applied, when the step input is applied, right, the input voltage is changing from 0 to VDD, the output voltage sees a VDD value. So VB is set to VDD, that means the VDS value is also VDD. Right, so now I have in the time t is equal to 0, VGS is VDD, VDS is also VDD at time t is equal to 0. At time t is equal to 0, the NMOS is now operating under which condition? Right, so if VDS is greater than VGS minus VT, then the NMOS should be in the saturation region. So it turns out that this VDS value is greater than VGS minus VT, so NMOS turns out to be operating in the saturation region. So that's what I've written, NMOS in the saturation region. Capacitor discharges with a current of the saturation current of the NMOS. And the saturation current of the NMOS is nothing but IDS, which is nothing but beta of NMOS divided by 2 into VGS minus VT, but VGS is anyways VDD, so it will be VDD minus VT the whole square. Right? So this is what the current equation says. So this is what the current of the NMOS, right? But the capacitance is actually discharging. So the capacitance is discharging, so that it should be the same. So this is the discharging capacitance, discharging current. So my IDS of the NMOS should be equal to that of the capacitor discharging current, and that's what the capacitor discharging current is given like capacitance multiplied by the change in the voltage with respect to the change in the time. So it is nothing but C dV by dt. C dV by dt is basically a charging current profile. So a discharging current profile will be nothing but minus of C into dV dV out or dVB of t divided by dt. Right. So what it means is, if there is a minus sign here, represents that it's a discharging profile. So the overall value of this minus C load into dVB of dt will be a positive value. So because VB is anyways decreasing, so dVB will give me a decreasing value, or will give me a negative value. So negative, and then here the negative here will neutralize it, and then we will get a positive value. Right, so the current here, I'm looking at a positive current value. Hope this is clear. Moving ahead, so now I have an equation of dVB by dt is equal to nothing but the saturation current equation. What we really want is the value or an expression for the output voltage, so VB. So this is what we want. So we want an expression for V of t with respect to time. Right, so what we want is a output node voltage as a function of time. Right, some kind of a function of time, so that I should be able to draw a profile of VB of t. Right, and then I should be able to extract the parameters. Right, it could be some kind of a profile. Earlier it was the one, and then it will be something like this. So this particular profile is what we want. So in this case, we will integrate the earlier expression. So let me go back a slide. So I have the saturation current, and then I have this this particular equation, and we want a VB expression. So I will take it, some of the parameters I will take it into the left hand side, and then try to integrate it so that I'll get an expression for VB. So this is what we have done. So moving those parameters on the left hand side, right hand side, I will eventually get this particular parameter, this particular equation. And then I'll put an integral sign. In the integral sign, I need to understand what should be the limits. The starting limits anyways is VDD for the output node voltage, right? And then at time t is equal to 0, that is where the output voltage is actually VDD, right? And I've written a parameter here t, so that means that from 0 to t, any particular point, any particular time, right, any particular instance of the time in the x-axis, the value will be VB of t, right? So I will start with the time t is equal to 0, that is where the output voltage is VDD, and then I will have the integration done up till any particular time instance, right? But knowing the NMOS characteristics, knowing the NMOS transistor, we know that this particular equation, which is coming from the saturation current, this is actually coming from the IDS of the NMOS of the saturation region. The saturation region is not going to stay for a long time. The reason is very simple. I have an NMOS transistor, so I'm drawing that, and then the input is nothing but VDD, the gate is nothing but VDD, source is anyways grounded. The output voltage is having a capacitance, it is initially charged to VDD, but now it is continuously decreasing, right? The input voltage is fixed to VDD, it's a step input, right? So the output voltage is continuously decreasing. So VDS value is continuously decreasing. So there will be a point where VDS will be less than VDD minus VT. So the saturation current profile is valid till this VDS or V output reaches to VDD minus VT. Right? Below that, the current of the NMOS will be in a linear operating region. Right? So this particular equation, the integral equation, this particular t value is applicable from 0 to a particular time till the NMOS is in the saturation region. Beyond that, it will go to the linear region. So in fact, this particular VDD value, this particular integral, so VB of t, I should be able to calculate, I should be able to express VB of t for a duration, right, from VDD to VDD minus VT. Right, so this equation is valid till VB is in between VDD to VDD minus VT. So that's what I have stated here and I have emphasized there. Okay, so getting from this particular equation, integral of this particular equation, it is pretty simple. This particular portion on the right hand side, it is nothing but a constant value, VDD, VT, beta n. Beta n again is nothing but if I write the beta n expression, it is nothing but mu C oxide W by L. All of them are the constant parameters. C load is again, is again a constant parameter. It doesn't vary with respect to the time, right? See, the capacitance, the load capacitance is a constant with respect to the time. So all these are constant. So I'll have an integral of 0 to constant into dt. So it is nothing but the constant value taken outside, and then the t variable. Here we have VB of t minus of VDD. So this VDD will come onto the right hand side, and this is what the expression I will get. Right? So this particular VB of t expression is valid from VDD to VDD minus VT. Right? So if I put at time t is equal to 0, I know that I'll get VB of t is equal to VDD. Right? Now, what should be the time where the saturation region of the NMOS ends and then it moves into the linear region? Right? So for that, if I put VB of t as VDD minus VT, the output as VDD minus VT, then I should be able to find out the t value where the NMOS transistor does the transition from the saturation region to the linear region. So that's what I have done here. So VB of t, if I substitute VB of t, the output voltage, to VDD minus VT, I'll get a parameter. I'm calling or labeling it as the end of the saturation region as T sat. So this is what I will get. T sat is equal to twice into C load into the VT, which is anyways 0.3 divided by beta n into VDD minus VT the whole square. Okay, hope this is clear at this particular point of time. Moving ahead. Right, so when the output voltage is less than VDD minus VT, that is when I reach the NMOS linear region. Right, my current expression, the current of the NMOS transistor is now different. It is not beta n by 2 VDD minus VT the whole square. Now it actually is a function of the VDS, and VDS is nothing but VB of t minus of 0. right? So VDS, whatever the VDS value here is nothing but VB of T. So my current equation, the current of the NMOS transistor is nothing but a function of the output voltage of the inverter. And that I'm going to equate it to the discharging of the capacitance, discharging current of the capacitance, which is nothing but minus C load into the first order of VB of T, the first order differential of VB of T dt. And then if I do the similar integral, the initial value, the integral of this, if I take certain parameters onto the left hand side and then right hand side, I'll get dVB of t, and then this particular whole expression onto the denominator side, I will get dVB of t, and then this whole voltage expression here on the denominator side, and then on the other side, I'll get this beta n, and then this C load is taken to the denominator side. So I'll get minus of beta n by C load into dt. The integral limits, because this equation is valid only for V out, beyond or lower than VDD minus VT. So my integration limits is this VDD minus VT, the lower limits. That is when the T is nothing but T saturation. And then the upper limit is nothing but the function itself, VB of T, and then time variable T. Right, so moving further, if I need to do this particular integration, so remember that if I go to the previous slide, this is one. So I'm just trying to see VDD minus VT is considered as VD of T, VDT, which is nothing but VDD minus VT. Right, VB of T, and then this is 2, this is not A, so there is a small correction, and then this VB of T. Okay, so what I've done, we have taken the partial integration. So I've taken the two parameters here, A and B. So what we have done is, so there is one particular function, and then we are trying to separate the partial fractions on one side of the integral side. So I've taken A divided by VB of T, and then plus B divided by VDD minus VT minus of VB of T, and that should be equal to our function on the left hand side. So this is what we have on the left hand side integral. So what we want is basically try to find out whether I can find out a separate fraction here and then separate fraction which will be equivalent to this right hand side parameter. Right, so if I want to do this, turns out that A and B value should be nothing but 1 by VDT and B is nothing but 1 by 2 VDT. Right, so if I do this, I mean it is kind of very simple to find out this A and B value. It is nothing but if I do the numerator and equate it to 1, I will get A into VDT minus A into VB of T by 2 plus of VB of T should be equal to 1 value. So A into VDT is nothing but 1 value. There is no VB component on the numerator side here, and that's why A turns out to be 1 by VDT, and then B turns out to be 1 by 2 VDT. Hope once you actually write it down, you should be able to find out much easier. Right, so now I have simplified that particular left hand side integral equations, and then A divided by VB of T, and then B divided by this particular denominator is equal to nothing but our minus beta of n C load into T minus T saturation. So this particular expression, if I want to do the integration, it turns out to be log of VB of T, and then this particular expression is nothing but log of VDT minus VB of T by 2 minus of 1 by 2, because there is a 1 minus of 1 by 2 here associated with my integral function. Right, and then the limits are nothing but VDT and VB of T. Right, again this is equal to this particular expression. Okay, moving forward. So finally what I've done is, so if you evaluate this and then if you find the solution turns out to be something like this, 0.693 e raised to minus 0.693 minus of beta n by C load T minus T saturation VDT. divided by 1 plus 1 by 2 and so on. Right, and then we have anyways calculated what should be the Tsat value, and if I put, if I use some particular parameters of the width of 1 micron, C load of 20 femtofarads, I'm just taking some values of the C load, the capacity, the load capacitance as 20 femtofarads. Mobility, I've considered it as, for a long channel model, we have considered it as 80 centimeter square per volt second. The width of the transistor is 1 micron, not 100 nanometers, it is 1 micron. So it is basically 10 times more than that of the primitive NMOS transistor. So the primitive NMOS transistor, in the 2:1 ratio, we know that the lowest width of the NMOS transistor should be twice that of the channel length, right? So the channel length is anyways fixed to 50 nanometers, so the width will be 100 nanometers for the primitive or the lowest dimension inverter. In this particular case, the width is 1 micron, so it is 10 times more. My beta n value turns out to be 5.26 into 10 raised to minus 3. So the Tsat value, if I put this beta n value here, C load value is anyways given, Vt is anyways 0.3. So if I calculate, I'll get 4.55 picoseconds. This is the Tsat value. Right, Tsat value is when the output voltage starts from 1 volts, reaches to 0.7 volts. Right, up till that particular time, NMOS transistor is in the saturation region. Right. So one more point here is to understand or emphasize is the V out of T here is basically an exponential profile, because on the numerator side also we get an exponential profile, on the denominator side also we'll get an exponential profile. But it is basically a decreasing exponential profile, right? And if I look into the, up till the Tsat value, so if I go back to the previous set of slides, so this one, right? So this particular equation, VB of T, it is nothing but VDD minus of constant into T. Again, so this is a particularly decreasing linear profile up till it reaches VDD minus VT. Right, after that, it is an exponentially decreasing profile. So the output voltage now, when the NMOS transistor is in saturation region, we will get a linearly decreasing profile at the output side. And then after that, whenever the NMOS transistor is in the linear region, we will get the output node voltage to be an exponentially decreasing profile. Right, so coming back to this particular slide, where we got Tsat is equal to 4.55 picoseconds. What should be the TPDF value? Right, now Tsat will give me only 0.7 volts. Right, so this TPDF value, so if I consider the profile, the output voltage profile with respect to time, it starts from, it will start linearly and then till 0.7. So this is a linear profile, and this is where we have got the Tsat value as 4.55 picoseconds, and then there will be an exponential profile. So this is the point of 0.5 volts. So what we need to find out is an additional duration from 0.7 to 0.5 volts, right? Where the output voltage reaches the 0.5 volts. So this additional duration plus 4.55 will give me the overall propagation delay. Right, so if I do this, so I have an expression now. So I am putting that particular expression of log of V out by VDT minus of V out by 2 is minus of 0.693 is equal to minus of beta n C load T minus Tsat into VDD. Right, so this expression is coming from our the previous slide where we had the log, the previous slide, sorry. So where we had, so this is the expression. Right, so I'm putting my using this particular expression, I'm trying to find out the TPDF. Right, so this is the slide we are in. So putting this V out as VDD by 2, because that is where the propagation delay falling definition falls. This is where the output voltage reaches to the 50% of the maximum output voltage. So the maximum output voltage is anyways VDD values. So the 50% of that will be VDD by 2. And so VDD by 2, and then we have this VDD minus VT minus of VDD by 4 minus of 0.693. So on this particular side, it will be nothing but this will be the propagation delay falling minus of the Tsat value. Right. So I will finally evaluate the TPDF as 7.72 picoseconds. So according to the long channel model. Right. So the propagation delay, how we have expressed this is, first we got the linear expression, linearly falling output voltage profile, and then an exponential profile. Right. And putting this in the exponential profile, whatever the expression is, if I put V out is equal to VDD by 2, I should be able to find out what is the time. Time is nothing but TPDF. Right. So looking at that overall timing diagram, so coming back to what I meant about the linear profile. So this is the linear profile. Right. So if I use a step input, of at the input side 1 volt, so that means that before time t is equal to 0, the input was 0, and then at time t is equal to 0, we have the input to be VDD. I will get the output voltage starting from VDD, because at input to be 0, the output has reached a steady state of VDD value, and then till VDD minus VT, till this particular value, it will be in the NMOS will be in saturation region. So I'll use the saturation current, but finally the output voltage will be a linearly decreasing profile. After that, it will have the NMOS region will be linear region, and we will get the current. We will use the linear region current, but the output profile will be an exponential profile, exponentially decreasing profile. And this particular point is our propagation delay falling. Till it reaches VDD minus VT, we have this Tsat point. Similarly, on the PMOS side, if we have the betas to be same, what we will get is a very symmetrical profile. Although it will start from, the output voltage will start from 0 and then reaches to VT value. So up till that particular value, we will have a linear profile. Sorry for this. This will be the PMOS. The PMOS will be in saturation. So when we have the input to be 0, right, the NMOS will be off and the PMOS to be on. So here in this case, what we had was when NMOS was on for a step response, for a step input, PMOS will be off. And when PMOS is on, that means when for the step input to go back to 0, PMOS will be on, but NMOS will be off. Right? So this particular symmetrical profile for the output to charge back. So this one was the output was discharging from VDD to 0. Now when the input voltage is 0, the output now charges back to VDD. So I will have initially the PMOS to be in the saturation region. We will get the linearly increasing profile, and after that we will get an exponentially increasing profile when the PMOS region is in linear. So sorry for that. In the slide I have made a mistake. This should be PMOS and not NMOS. Right, and then we will get a profile till it charges to VDD value. Okay, so hope this is clear at this particular point of time.